So you guys have the midterm, like I I I don't know. Um, so what you guys expectation on the midterm? Like, so typically this kind of midterm, I don't expect you guys to really do really great, like on average. So actually, maybe give you some number like out of 40, like if like 40, like, and the average is around 20, if I remember correctly, 20 something, 21 or 20 something. This is a mean, uh, and the standard deviation is like 10, so it's like quite a bit fluctuated. Um, and I'm thinking to try something new this semester. Like usually I just like have a class to talk about the entire solution, but then I guess that there's not a lot of incentive for you to really study the solution and so on. And probably I talk about that, you feel like quite bored. Um, so instead I'm thinking like, uh, so unfortunately not all of, most of you, like many of you guys are not here, but like as you see, I already posted another assignment. So it's like due like next Saturday. So this is like, it's not exactly assignment, just a correction of your midterm. So you can just submit a correct solution there. Oh, hi Dylan, this one more guy, that's great. So you can submit a correct solution like for your midterm. Um, so I will just look at like uh, if as long as you are doing better than your original solution, like you will get some credit for that. Like of course you cannot get all credits. What I have in mind is that I will give you 50% credit. So for example, if you get complete zero like this time, then like if it turns out your correct solution is like 40, then you will get like 20 back or something like that. Like this. So um if you want to, yeah, submit a correction, feel free to do that like by the end of next week. Then I probably won't talk about the solution like for a while or like for the meanwhile, and only talk about that. If you need to ask me anything besides the exact solution of the question, like of the midterm, like you can pass me any questions like in Discord. I will try to uh, for example, if you ask me some general questions like what is actually entropy really or something like that, like very generic questions, I'm happy to answer you. But of course, I cannot answer you precisely what's the solution of particular question. Then it will defeat the purpose of this thing here. So is that clear? So then what I'm going to do first then will be um, I'm going to continue to talk about channel capacity, the proof of channel capacity, at least the forward proof of the capacity. To do that, like I need to talk about, so wait a sec, I better pull out you guys chat. Um, Maybe I put here, yeah. So where's it? Sorry, I'm looking for my, um, probably it's better just use search. Okay, so so we mentioned last time is a okay, maybe first we talk about like what we like to talk about today first. So we I'm going to talk about the forward proof of the channel capacity theorem. So channel coding theorem. So essentially, if you have like a channel defined by the conditional probability distribution. So if you have an input x and the output y, for simplicity, I would just assume like x and y are discrete random variable. Then like the capacity of this channel. So when I mean capacity, we'll be saying like, okay, if define something will be some kind of channel, and I can say like given a message here, I'm trying to code the message and pass through this channel. So let's say I for each message, I say as I mentioned, just a review. Like I have M message here, and let's say like for sending this one of these big M message, I'm use this channel n times. So I will transmit a sequence of length n, and then at the decoder I have yn here. Then I have a decoder, and I trying to recover like the message I'm had here. And the goal is like I want to make sure that the probability like m hat is not equal to m, so it goes to 0. And the transcoding theorem is saying that, oh, this is possible to do that as long as the weight will be defined as like the number of message here in terms of bits, that will be log n, your base 2 here, over the number of channel user over n here. As long as this is less than the capacity, then we can make sure we can find a scheme such that like, you can transmit this message losslessly through this channel. And this capacity is basically just the mutual information between x and y. And of course, it depends on the input distribution. This is something I can control. So I will try to that. So in the sense, it would be something like that. The expressions would be something like that. I mean, like if you look at this, we're very intuitive, right? How much I can transmit through something here will be simply the mutual information between them. But at the same time, here I can control the input distribution. So therefore, I can the maximum amount of information I can pass through that will be the maximum of this mutual information with respect to the input distribution. Now, this is what I'm trying to show today, at least in the maybe first half of the class. In going through that, like, I need to introduce something known as the packing lemma. And also I will talk about like something very similar, the covering lemma. I'm not going to use covering lemma, but if in the future you're going to study weight distortion theorem, so this thing is I will skip like for this course here. If you're going to talk about weight distortion theorem, so you need the covering lemmas to prove that. So, but because they're so similar and or I would say they're so related to one another, I think it's good to, when I mention packing lemma, I'm going to mention covering lemma as well. So what the packing lemma and covering lemma say is that said is that if I have I have like a okay, I guess I need to remind also this is something like about like channel capacity, but I need to remind also like join the typical sequence, join typical sequence. So join typical sequence is like essentially extending the idea of like typical sequence, but for typical sequence I only have one source where I have a px, and in the sense like everything I'm drawing from this set here, if I join a sequence, this sequence will be typical. So, and typical, you can think of like this, the probability by law of large number will be approximately 2 to the minus n hx. So joint typical will be simply, I have a joint source here like pxy, and I'm going to pull out like sequence xn and yn, and they're joint typical if like each of these xn and yn is self-typical, so therefore like pxn will be like 2 to the minus n hx, and also like pyn is a 2 to the minus n hy. But also like the joint probability like x and yn will be approximately 2 to the minus n xy. So by very similar argument, we can very easily show that like any sequences pulled out for this from this joint source will be jointly typical. And the number of jointly typical sequence will be approximately 2 to n hxy. So that's like the set, let's say this a epsilon xy, I call it like n. The size of the set, the number of joint typical sequences will be like that. And maybe I erase here to get more space here. And more precisely, will be I have something like joint typical will be like pxn yn will be bounded by 2 to n hxy minus xy minus epsilon less than equal to 2 to minus n hxy plus epsilon. So yeah, this epsilon is like just, it's like some kind of like dummy variable in calculus. It's it's useful for analysis, but conceptually it just make the math rigorous, but conceptually it doesn't add anything new. I'm also like using this, I'm using like argument as we show the size of the typical set as before. You can show that the size of the typical set for the jointly typical set will be bounded by like 2 to n hxy plus epsilon and bigger than equal than minus, let's say 2 to n hxy minus epsilon. Note that, however, like there's a kind of a small caveat here. This will be a 1 minus delta here. Again, like this is like some kind of like minor technicality, like it's conceptually. If you go through the math carefully, you see like why there's a 1 minus delta, but it doesn't really matter too much. So, but that's something like actually basically the only thing you will need to know, and is something like also pretty intuitive for us to prove the channel capacity theorem, and also the packing and covering lemma. So what does the packing lemma like saying? So for the packing lemma, what it's trying to say is like if you have like let's say you have like py that pull out a sequence yn here. Maybe I pull out a random sequence, maybe I use cap here, pick yn here, and then I also like from px, I'm going to pull lots of sequence like xn here, maybe first xn1, xn2, and so on, like a number of sequence here. So what the packing lemma is saying is that how many of this sequence I can pack together with this yn such that none of this sequence will be jointly typical with y. So of course, here what I start with is like this x here is actually independent of y. If I have like they are actually coming from a joint source like yn and xn, then of course they will be like jointly typical. So you put one of them already, they should be jointly typical. But if like as I'm showing here, y and x originally are independent, then they should not be jointly typical to start with, right? At least you guess there's no need that they should be jointly typical to start with. Now, and also like the next question to ask is like, how many of this sequence I can put together with this yn until one of them will be jointly typical with yn. That's a packing lemma. And for the covering lemma, it's like very similar. For a covering lemma, it's basically if I have like same thing here, ym xn here, x and 1, and so on and so forth. Now, what instead is like, I'm thinking like continue to add number of sequence here. Yeah, that's fine. So, okay, one thing, yeah, Mohammed, I'd like to mention, like, yeah, maybe you can look back. Like, I introduced a kind of like an assignment, just a correction of your midterm. If you want to submit like a correction that like you can get some extra bonus. So you can look into the description, yeah, on Canvas. So okay, okay, go back to this covering lemma. The covering lemma is basically saying that like if I'm going to now if I'm going to like get more and more sequences here, like independent sequencing here, I want to know like how many number of sequences I need to pull from this PX until like at least one of them will be jointly typical to this one with YM. So the result is quite interesting. Turns out the result will be more or less like the number of sequences here will be, for both of them, will be approximately 2 to the NIXY, I think. Let me see. Yeah. So basically, so for both cases, you have like a similar to this like a phase transition in physics like that, like phase transition phenomenon. So as you add more and more XN sequences here, originally none of them is going to be like jointly typical with YM, but when you reach like the order of like 2 to IXY, uh, whenever you pass that, you'll be sure that like one of them will be typical, jointly typical with YM. So we're going to give a quick proof of these two guys. Actually, I gave kind of like several steps of the proof of the packing lemma like last time, like near the end. But however, I forgot like I missed an element to show that. So then I I guess I will just fill that in now. Basically, like one, I'm not sure. I should say a lemma or something like maybe to call it lemma here. Another lemma, a very simple lemma here. So if I have like simply two of them, like px and py, only point one sequence here, xn and yn, and again, like both sequence here are independent to start with. So the question is like, what's the probability that like xn and yn are jointly typical? Maybe I put it this way. So if like xm and yn are from the same source, if like it's actually pulling from same source here, then you know the answer already. Like this will be okay. I don't know whether maybe I will just pause here. If I'm going to, this would be a simple question. If like xm and yn is drawing from the same source here, what should be the probability of this guy? Yes. It's just a kind of like show. Just want to ask you to see if you guys are here. Yeah. If xn and yn are drawing from the, it's not the same source. Are drawing from the joint source. Then it would be just like the, then more or less from the argument of like jointly typical. You should always like you will find a joint probability like for this guy like pxn yn. We'll have probability like more or less equal to 2 to the minus n hxy, something like that. Will satisfy these conditions here, so therefore will be jointly typical. So, but of course, the thing is, yes, that's a question here. So now that's what we try to see. Like, if the lemma here is like, if they are from independent source, like x and y are independent. But, okay, maybe I need to elaborate like, a bit, like what do I mean by independent. So it means that like you can think of like you start with a joint source here. Now you're going to this joint source, of course, you can put some x and y here, right? Y and here. You can think of independent as like maybe for the first like n time steps, you pull out, of course, a pair of like x and y together, right? But you just discuss y, right? You forget about y. You don't get y. You don't work out y. Just take the x. So you have xn here, and then and the next n time instance. So like this is a first n instance, and then for the next n instance, you're going to like, so you have like pull x and y n here, but you ignore xn here. For the next n instance, you also draw x and yn, but this time you discard like xn, you just only keep yn. So in this sense, like this xn and this yn should be independent. Okay. So this is just one example. Of course, you can get other example. For example, like you can have, even you don't really have a joint source, but you really have a marginal distributor. You have a px here, that this px turns out to be equal to the marginal distribution like pxy sum over y. So you can construct that like by many other ways, like whatever ways you want. And then you pull out the sequence xn here. And similarly, you can have a py that is like, that just simply the py is equal to marginal of the original joint distribution pxy there. And then you draw a yn, then this will be independent as well. And you want to see like how what's the probability these guys will be jointly typical. So the lemma is saying that like in this situation, the probability that like xn and yn will be jointly typical is like kind of like bounded by, actually to be more precise, will be bounded by 2 to minus n rxy. Actually, it would be like some epsilon here also, but yeah, this kind of epsilon just something like, again, like some characteristic like you can ignore most of the time. So conceptually, the important part is it's like proportional to the ixy, to n to the ixy, to the nisy, to the minus nisy. So we are going to prove that. So first we look at this here, the probability xn and yn to be jointly typical. So the thing you can think of like this one will be simply equal to think like that, like you have like a number of sequences to be jointly typicals, right? So xn and yn, like you think of like all the jointly typical sequence and think of like what's the probability of this jointly typical sequence, and sum all of them together should be equal to this probability, right? In other words, like think of like all the jointly typical sequences xn, yn, or the jointly typical one, and sum over the probability of each of them. So this should be equal to this probability here, right? Now, this one, because x and y are independent, right? So therefore, this should be equal to like x and y and px and pyn. So these guys are independent, but they are still typical when they pull. I mean, they are not jointly typical, but each of them are typical. So therefore, like they will be bounded by okay. I hope like I find that myself like getting farther and farther away from the mic. Hopefully, it doesn't hurt. So it's bounded by like 2 to minus n h x. Let's see, minus epsilon, and this will be like bounded by like 2 to minus n h y minus epsilon. Right? And then this thing now is just a constant, right? With respect to x and y, and like right, this does not depend on this is like really a constant with respect to individual x and y. So I can pull it out. So it's equal to this multiplied by sum of this guy, right? 1, right? And what is this? Like, what is this? Like, can you describe what is this here? Oh yeah, maybe I write it more clearly. So let me write down the whole thing. So I pull this out here, 2 to minus n h is minus epsilon to the minus n h y minus epsilon, and then I sum over x and y and a epsilon times 1, right? Because this pull out, this is just a constant, right? So what's this? um, no, you need to be a bit more careful for that. Look at the sum here. Like I'm not summing over n of yeah. mm, yeah. Okay. Is that now better? Like hearing me because I maybe I earlier like I move a little bit away from my mic like as I change my kind of like posture. So oh, actually, each exam has much more item than that. Like if you think of exam, like if I don't have any constraint, think of the alphabet size is n, then let's say sorry, the alphabet size is squid x here, let's say. Then for all the combination of xn should be like x to the power n. Yeah, but that would be too big though. So if you look at that, if I don't have any constraint, probably it will be like x to the power n, y to the power n, something like that. But note that I have a constraint here. I'm only considering sequences. They are jointly typical. So then this should be essentially this is just counting the number of jointly typical sequences, right? So actually, you can, I think you can find the answer on the slide here, on this page here. But I guess it's a little bit, maybe could be a little bit hard to read. But I just gave a hint like a moment ago. So this should be bounded by the number of like jointly typical sequences, right? And this in terms is bounded by what? Mm, mm, oh, okay. That's close, but that's the lower bound, and that's have a term here also. Right. And for 1 minus delta here. Yeah, no, that actually we don't want to change the direction of our like inequality here. So we're looking up for the upper bound. So I guess I will just continue here. So I'll just answer my own question. So this will be bounded by this guy here, right? So it's a bounded by, so bounded by 2 to n h x y plus epsilon. So combine all together, you see like this will be like 2 to the minus n h x plus hy minus hxy and minus 3 epsilon here. And by this time, you should be quite familiar after the midterm that this one is equal to what? Yes, 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 yes. um, yeah, this is actually it's also show here, right? There's a that's exactly what we're trying to show. This is a big bounded by ISY. Yeah, that's done with our proof here, right? So, kind of in summary, so if you have like if you're drawing like kind of like two independent sequence, like if you have two sources like px and py, you're kind of like these two sources are independent, and you are drawing two sequences of them separately, then the probability for them to be jointly typical uh, will be like 2 to the minus n ixy. And this is something useful that, or like it's bounded by, upper bounded by 2 to the minus n ixy with some epsilon here. And this is useful like for us to show the packing lemma. Okay, let's see. Maybe I can erase here. I'm not sure I have enough space for my packing lemma. Let me see about that. um, so okay, let's try to show the packing lemma now. Maybe I change the color. I don't know. Like it's maybe easier to read. Now trying to prove the packing lemma now. It's like the packing lemma is saying that okay, how much of this is needed, right? So basically we are saying that like if the number of kind of like x here is less than 2 to n xy, then we are good. So if like it's less than this, then we are good. um, so now for packing lemma, think of just that. Like let's say the probability I have, let's say like here let me here let's say I draw like m sequences here from xn. I want to see like what's the probability that like all these m sequences let me write like this, or xn 1 xn not jointly typical with yn. But actually, easier probability to consider is like the 1 minus of this probability. 1 minus of this probability will be the probability that one of the xn 1 xn m, I have big M here, I think, is jointly typical with yn. Right? So as long as okay, if I say one of them, so if I have one of them, let's see, one of them, any one of them to be jointly typical with yn go to 0, then I'm good, right? I'm happy about that. Yeah, that means that like I can pack all of them like into with yn here. Let's see, did I make the logic incorrect? Let's see. Yeah, I think that's right. Yeah, okay. So now we look at this probability here. This probability will be basically like each of them are independent, right? So that actually is very easy. Like we have like for any one of them to be jointly typical with yn, it's a basically is probability, let's say, what is say x and let's say just I, or maybe I just write xn, simply xn. Okay, maybe I write like this. It's like equal to the product of like probably x and I jointly typical way. So because they're independent, they will be like just like okay, the one of them are jointly typical with yn will be equal to probability that like the product and product of them. Oh, actually, wait a sec. Wait. This is incorrect. This is incorrect. I'm so sorry about that. Yeah, I cannot really say that. But what I can say is like I can say like there's a union bound here. So one of them are jointly typical with yn will be bounded by the sum of the probability each of them to be joined together. So this is like something like union bound. So it's like instead, like for example, if you think of like uh, what's the basically this one is more or less like one of them are jointly typical with yn. So for example, if I just consider m equal to 2 here, so let's say if you draw a set diagram here, so the probability for either one of them are jointly typical with yn will be like, let's say this one is like jointly typical with yn, this circle is like this is x1 jointly typical with yn. And this one is like x2 jointly typical with yn. So then either of them jointly typical with yn would be like this area, right? So and then of course this area will be less than the sum of like this probability, like each of the circle here. So therefore, like therefore I have this this union bound here. So you agree with that? So with that, then it then become very easy because I know each of these like what is that like from our previous lemma, this is bounded by like 2 to the minus ni xy minus 3 epsilon, right? And am I here, like I is from 1 to m, right? So I have m of them is bounded by this. So then what you see is like if I have m is I weight as a 2 to n out, meaning that like I will because m is the number of message, right? If you write it in terms of weight, like m will be represented by 2 to n r, right? So then I can write it as a 2 to the minus n I x y minus r minus v epsilon. Here, m is 2 to n r. So here, just think of like you kind of like substitute m as a 2 to using as substitute variables. So instead of like m, that is basically number of messages, think of like the weight instead of like using the unit weight here instead. So then you see that like then as long as my weight here r is less than ixy minus 3 epsilon, then I'm good, right? Then this one will go to 0 as n goes to infinity. And that's basically the proof here. So of course I can make this again, like this epsilon here is something arbitrary. We can make it arbitrary small for epsilon. So even though there's like minus 3 epsilon here, that's fine. You can just consider this like not existing here. So then the conclusion will be essentially like whenever your weight is less than the mutual information, then the packet lemma is saying that like the 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 number of messages you can pack along with yn will be bounded by like ixy. Okay, that's very mouthful to say. Let's see. So this is like 2 to n r or something like. If I write this like instead, okay, let's write like that. Instead of writing 1, 2 up to instead of thinking of n messages, think of like I have 2 to n r messages. So then okay, and then if I write like this, as long as r is less than ixy, then I can make sure that like none of this x here will be jointly typical with y. So that's basically the packing lemma. So let's see. Let me see if I can. Okay, maybe maybe I will use the same space here to show the covering lemma. So immediately, let's also like quickly show the covering lemma. Basically, the covering lemma is saying something like if I have something like maybe also write the conclusion here for the packing lemma. I'm feeling that maybe you guys so yeah, I guess it's actually okay. Now let me just do like that again. xn1, xn and 2 to n r. So if r is less than ixy, actually that's like some minus 3 epsilon here, but it's not important. Then probability xn 1 yl. Ln of x and jointly typical with yn goes to 1, something like that. That's the covering lemma, that's the packing lemma. So for the covering lemma, it will be like very similar, but instead, like essentially, I can use the same picture here, But now, if R is bigger than Ixy plus V epsilon, then probability that one of xn jointly typical with yn goes to 1. So let's see if I can use the same space to show that. So that's, as I mentioned like earlier, this is like some kind of like phase transition in physics, right? In statistical physics. So as long as like this weight is like just past this Ixy, suddenly like you have a phase change from none of your sequences like jointly typical to yn to like one of the sequences must be jointly typical with yn. So let's quickly also show the covering lemma. Then we maybe just give a proof for the transcoding field. So for the covering lemma, okay, for covering lemma, I have, let's say I want to consider like the probability that like none of them, okay, taking this probability is a bit difficult. Again, I am consider the negation of this one. Instead of considering like one of them to be jointly typical with yn, consider none of them to be jointly typical with yn. So let's say like I have xn m yn. So let's say like all of them are not jointly typical for all n, for all m. So I want to see like okay, maybe I need to pause here also. What do I want to get? What do I expect here? If I want to show this covering lemma, what do I want this to be? What do I want this probability to be? Let me give you some hint. 1, 0. Yes. Okay, half and half. Note that this is an exact opposite. Like this thing, this is a original statement. It's like one of the exam has to be jointly typical with yn, right? I want this probability to be 1. And if you look at this event here, like one of them to be dropping to yn, this is kind of like the exact opposite of like, yeah, all of them not jointly typical, right? So yeah, that should be 0. Yeah, I want these guys to be 0. So I look at this guy, like, let's see, like, under what condition this would be 0. So, and this one here, I can write it as, now each of them is independent. Now this time I can really write the product. I write product as a product of like x n and y n, not typical, not jointly typical. M is like from 1 to m, big M here. Now the probability that like this guy are jointly typical is just 1 minus the probability that to be typical, x and m, y n to be typical. And product of that. And the probability that this one to be typical is bounded by, so I want, okay, by the way, like this one, let's see, like what do we want? We want this to be 0, right? We probably want to get a upper bound for that, right? Eventually this upper bound goes to 0, right? So I want to say like what is this thing is upper bounded by. Oh, actually, oh yeah, sorry. I didn't show this thing here. This guy here, I only show this side here, but you can show the other side. Yeah, you by the same argument like of this thing, and also like this thing here, I can show that this one is this term here is lower bounded by. Let me move it here. This is like bigger than equal to 1 minus delta 2 to minus n I x y. Sorry for my handwriting. Plus 3 epsilon here. Yeah. So okay, I will use that because I want to get a upper bound for this guy. This is like negation of this thing, so therefore I should look for a lower bound of this term here. So I can say this is like upper bounded by 1 minus delta 2 to minus n I x y plus 3 epsilon here. And now this become does not depend on like m here. So therefore like I can really this guy like just say multiply this term here m times, right? So therefore I can really write this as like this thing to the power m instead. And so now if I look at this guy here, know that like this one it's I can use a very simple inequality here. Consider inequality 1 minus x is less than equal to e to minus x, I think. So it's something like if you go along the range of 0 and 1 minus x will be something like this. E to the minus x, let's say this is 0 here, let's say, so wait. 0. So this shouldn't be 0 here. So let's say here is 0 here. Wait, actually I 1 minus 0, yeah, 1 minus 0, 1. Actually this is right. 0 is here. So when x is 0, then it's 1. X is 0 here. Oh, sorry, like let me say again. For the left hand side, when x is 0, like 1 minus x is 1. So it's like this point here. And for the right hand side, it's the same thing, right? You have like x is 0, e to the minus 0 is 1. So we start with the same point here. But 1 minus x is going like this, right? But you know that like e to the minus x is actually is something like convex. And so therefore you have like an inequality like that. And you can check the slope here is the same, right? So therefore the tangential at the point here. So therefore like you definitely have this guy is above this one here. Now I will just use this simple inequality here. So then I consider this, maybe I don't call it x here, it's like confusing. Maybe I call it a z here. So, and I can think of like this part as z. So then you see that like I will have 1 minus this one is like less than e to the, maybe I just write exponential minus 1 minus delta 2 to minus n I x y plus v epsilon. Let me erase this c here. And I still have an exponential m here, exponential m, but exponential m, of course, I can absorb into here. So it's like it's equal to exponential m times this guy here. And again, I take m as 2 to the n r, then this will become like exponential minus 1 minus delta, let's see, 2 to n r, 2 to the 2 to minus n, or maybe I write 2 to n here, 2 to n r minus I x y minus v epsilon. Okay, it looks a bit ugly, but if you look at that, the point is like, if I have r is bigger than like I x y plus v epsilon here, then this guy will be positive, right? And n goes to infinity, n goes to, if n goes to infinity, then this term here will goes to infinity. So then this whole thing goes to infinity. So therefore this will go to 0 as n goes to infinity if like r is like bigger than like I x y plus v epsilon. So okay, that's basically the proof for the Coupling lemma. So in conclusion, okay, like let me repeat like a couple of times again, like this is important. So you see, like I just have a threshold like this, like the number of ixy, number of like sequences I can pull from this exam will be like just 2 to n ixy, more or less. As long as I have less than 2 to n ixy, then none of the sequences will be jointly typical with yn. If I have more than 2 to n xy, then some sequences will be jointly typical with yn. I'm for sure that I will be able to find one sequence, one xn sequence to be jointly typical with yn. Okay, yeah, so that's basically proof for coupling lemma and packing lemma. So then now I'm going to use that to show the channel capacity theorem. More precisely, I'm going to use the packing lemma to show the channel coding theorem. So yeah, maybe I can erase the capacity. So in the coupling lemma now, so we are not going to use it for the time being. Actually, probably like for this, the rest of the course, we are not going to use it. So, but I guess it's good to mention it here because they are so related. So now for the covering lemma, sorry, for the packing lemma, we have this way. So as long as like is less than 2 to the n ixy, then I can make sure that xn and yn are not jointly typical. Now, how do I use in here in the channel coding theorem? Let's see. So okay, let me start from here. Maybe just put it here. So I'm going to give the forward proof of channel coding theorem. So so basically what we are going to do is that we are going to create a random code. A random code in the sense that like, okay, I think of like this is a px. Oh, okay, of course the capacity here. Let me write down the capacity. Capacity here is equal to ixy maximum. Why is that I cannot write it? Over px here. Now let's consider like let's say px star is the one that maximizes the capacity. That's basically the arc max of ixy here. Oh shit, I suddenly cannot write. Okay. Huh? What happened? Okay. Now I'm going to just consider a source here, px star here. And I'm going to generate a codebook this way. I have a random codebook. Like out of this source like px star, I'm simply going to pull sequences out of this px star. So let's say for the first code word, let's say I have like m messages, right? I have message 1 up to message m here. For message 1, I will just pull it first time, like I will have like x1 here. Let's say a sequence of length n again. And then for the second message, I'm going to like sample this source again. And then I have like another sequence here, x2m, and so on and so forth. Then I have like the entire cobalt drawn randomly, like with like now I have m sequences like as the code word. So then the encoding and decoding is very simple, like I mentioned that last time. So encoding, like if you receive m here, simply output x and m if input is m, if the message is m, right? It makes lots of sense, right? So you have a combo like that. That's basically if you have message m, just send out x and m here. Send out the respective code word. For decoding, what we are going to do is say, of course, at the decoder, I receive a yn, right? I receive a yn here. Basically, what we are going to do is I find xn such that xn yn jointly typical. So if they are jointly typical, let's say if it's jointly typical, then I would say the message will be m, right? Know that like I don't know. Okay, maybe I write m hat instead. Like so, I mean I may have sent m here, but I only receive yn, right? I don't know what's the message, original message. I simply go through the entire code book and see like which one is jointly typical with ym. And if like one of them is jointly typical, let's say if m hat x and m hat is jointly typical with yn, then I simply say the message is m hat. So then there would be some error events here, right? So error event like error actually will be bounded by two cases. Probability of error. I will say P1 and P2 here. So P1 will be like if my M actually time is not jointly typical with Y, or what I mean, the message, let's say the message is M here. if x and m, of course, if I'm need to be decode that m hat correctly, I should have like x and m to be jointly with in, right? So therefore, first error event will be like probability that like x and m and yn are not jointly typical. So here, of course, I'm assuming that I'm transmitting m at the beginning. But okay, this goes to 0 because if I'm transmitting x and m, I mean like if I receive a message m here, and my encoder is transmitting like x and m here. Maybe I draw like that. And this x and m is like going through, actually going through my channel at pyx here. And then I'm going to receive this yn here. So this x and m on y and yn is like coming out of a joint source, right? In this sense, like, because this is like the joint distribution, like this is marginal, this px here, this whole thing is just pxy here. So it's essentially I'm just having like x and m and yn is coming from a joint source. So therefore, like by the law of large number, this pair has to be always jointly typical. So therefore, like essentially, I can ignore probability. I mean, the error event one, the probability should goes to 0, as long as n is sufficiently large. Now, for the second error event, it can be if I have some other m, it says m hat not equal to m, such that x and m hat and yn are jointly typical. And if this happen, then we'll have error as well, right? So maybe I will pause here, like just for a sec, like. So what is this? Can you tell me what's this? Let's say I have m messages here, or like approximately what is this? Yes, yeah, it's yeah, it's close. Yeah, it's related. Like yeah, it's definitely related. Um, yeah, I guess it may be like a little bit challenging because I erased the proof of the packing lemma. Um, um, this is, if you look at this here, this is exactly um, the the probability like we study like in the packing lemma, um and if the number of like if the message a number of messages m, or like if I write m as like 2 to n out, then actually yeah I'm yeah kind of, yeah, I guess it's not easy like for you to see it here, because I erased the proof here, but that's precisely the probability is the conclusion of the packing lemma probability. That is basically will be equal to this will be like bounded by like 2 to n minus n r minus I x y, something like that, like minus v epsilon, something like that. So as long as you let's see, let's see, it's really say minus or plus. I think it's plus. Let me go. Yeah, but okay, like it does, forget about this epsilon here. So I guess I flipped the things. Like, let's see. Or like I can remove this minus sign. That should be good. So as long as my weight, let's see how yeah, I think this is better with this way. Yeah. So as long as my weight is less than ixy, then the probabilities will be going to 0 basically. So and this is like, yeah, okay, like sorry, I erased the proof. Like that's the line I need that for the proof actually. But you can also see it here, right? This is essentially like this P2 here is essentially the probability of this probability of error is essentially the events that like you have one of these independent sequences to be jointly typical with yn, right? Because I have this m of them. I have like this m sequences, and from the packing lemma, we're saying that like as long as I say m is equal to 2 to n r, if r is less than ixy, or like if like m is less than like 2 to n ixy, then none of them will be jointly typical with yn, right? So then like this probability will goes to 0, right? So therefore like maybe like simply like forget about this probability. From packing lemma, oh, I cannot write for some reason. This is so weird. From packing lemma, P2 goes to 0 if IXY is, or let me write. R is less than IXY. And so, and of course, as long as this IXY here, because I pick like P star here, that's like the probability that maximize the capacity. This is actually equal to capacity. So therefore, like as long as I have my weight is less than capacity, this kind of random code will give me the performance say that the error of um of of the decoding errors to be to goes to arbitrary small. So, but there's some caveat here, but I will just probably leave it like here, like I'm talk about that after the break. So let's take a break for like again 15 minutes. I will my clock is like 4:18. Like let's come back like 4:33. So I will see you guys like in a bit. Yeah. Yeah. Okay, I guess we'll continue. So again, like maybe I repeat a little bit. Like the fourth proof is simply saying that I'm going to have this random code that is a each of this code is joined from this p star x here to get a code words like m different code words here. And then a encoding will be just receiving a message m. I will send out the code word like when I have a message m, I'm going to send out a code word of x and m here if I message m. So, and I get the decoder, I receive yn, I'm simply look for the one is joining typical with that, and then I'll output m hat if like x and m hat is joining typical with yn. And the error event is I just first is like if I have if the original message is m but x and m and also yn is not joining typical, then this will be an error. But by law of large number, this won't happen. Basically, this will go to 0. The error event is like if I have another sequence that is not basically m hat is not equal to m, but it's not but it's jointly typical with yn there. So, but by packing lemma, we know that as long as we're not packing more than 2 to n ixy of them, then we should be fine. Then this probability will go to 0 as well. So therefore, like because ixy here, the probability p we are considering here is the one maximizing like ixy. And so therefore, like this ixy here is actually equal to capacity. So therefore, like we can reach the capacity kind of as long as like our weight is like infinitesimally smaller than the capacity. So okay. Here like I just want to say a caveat here though, like in this argument, like there's a slight caveat here. Everything is fine. But if you come to think of that, like what we want to show is really like we want to find a code, like maybe I write C star here, such that like the probability of error, maybe I just write like that, like error given this C star, and for any message M should goes to 0. That's our target. That's our goal here. But because of the random code I'm using, what I'm really showing is something like that. I have probability of error given C, not C star, given some C here, and M, average over all the C here, all the random code here, will goes to 0. So this is what we show. So okay, if you look at that, like one thing you think, okay, since like the average is going to 0, then we can argue that definitely have the C that with the smallest probably basically saying that this thing here, like this is the average, right? This average, I say, is equal to delta going to 0. If the average is equal to delta, then that must be like the best one, the best C star. I should have the probability of error C star M will be less than delta, should also go to 0 as well, something like that. But this again, I have a issue for this argument here because if I say like what's the C star here, this C star will depend on my message, right? I will have like C star M, I have some C star M here. M will be less than delta. I'm going to 0 here. Now, but of course I cannot have like each different message have different code book. I need to have like one code book. Like basically I cannot have like here, like this C star actually depend on M, meaning that like each time I receive a different message, I'll use a different code book. Then of course this is not what I want. So, but I can still work around with that, work around of that. So what we can do is say, okay, think of let's remove this delta layer. I'm not going to use this delta here. I'm going to use delta again like, for other things. So this is what I show. This is equal to 0. Now, if this one is equal to 0, then the average over the message as well will go to 0 as well. Right? If I also take the average over the message, this will go to 0 as well, right? So this is a stronger condition than this one I've written here. Then of course this will go to 0 as well. And I can flip this, the sum over. I have like PC here, PM, let's say. Let's see. Okay. I want to make sure. Sorry. Wait a sec. Yes, I can write like this. Okay, let me just npm pl cm. Okay, I'm not doing anything. I just flip the summation here. But now if I look at this here, this is I'm doing an average of this term here, right? You can think of this as a some function in terms of c. I'm taking a kind of an average of this one. Then of course I can find one of this c that is a will be have a better performance than the average itself. So in other words, like I will have something like this one. Have something. This one will also go to 0 as well. And for this C star, this one, let's see. I will call it this one delta. This time I'll call this delta. Let me call this delta here. This one will go to 0. And now for the message, like message probability, let's just for simplicity and without loss of generality, I assume like the message will be used like with equal probability, like they appear with equal probability. So therefore PM will be just equal to 1 over epic gam here, or like equal to 1 over 2 to n out there. So I have PRR C star and I have something like that. It's like equal to delta. This goes to 0. Now what I can do now, like think of like here I have m messages, right? Let's say m is equal to, just give a number. Let's say m equal to 10 here, or maybe give a better number, maybe a is a power of 2, m equal to 8 here. So I have some is better, some is worse. The averages are equal to delta. So if I sort them, like solve the probability of error, Let's say I have 8 of them. So the average is here, right? So if my average is here, then if I just pick the best uh, 4 that have like smaller error, this I just take this 4 here. Um, the if I just use this 4 here, the probability of error cannot be bigger than, let me see. I'll claim that like if I only take this 4 here, consider this 4 here, then any of this remaining message, I will have like probability of error of like any of this m here. Note that I'm not looking at average now. For any of this remaining message, the probability of error will be bounded by 2 delta. So it may not obvious at first, but let's think about that. So let's say if I have one of this, let's say I already sorted this, maybe a little bit hard to see. If you look at this error here, right? If I have the average is equal to delta, let's say if I have like this one of them one of them is like bigger than delta, bigger than 2 delta, then the rest of these other guys has to be bigger than 2 delta as well, right? And if you think of the average, like out of this, the average will be equal to what? Okay, let me write it clearly. So yeah, let me just use like this example, like m equal to 8. So if I have like this one, what I'm arguing here is like, I'll say if I take the best 4 messages here, that if I just look at these 4 messages here, each of them like cannot have error more than 2 delta. Because if otherwise, like if they are like one of them, okay, the one of them, let's say this one is bigger than 2 delta, then the worst half of that 4 messages must have like probability of error like is larger than 2 delta, right? So this guy will be already bigger than 2 delta, each of them. And if you think of like the original average is equal to all this sum together over 8, right? And this guy, just look at this portion here. This portion will be the sum for this portion. Okay, if the average is equal to delta, the average will be the sum will be equal to m delta, right? Or in this case, you can do a delta, right? But if I have like these guys here, all of them are bigger than 2 delta, then just sum over these 4 guys here, I will already have like the sum is bigger than 8 delta. So therefore will contradict with the original assumption that the average is delta. So, okay. And then you see like, okay, that basically it. So what we can do is like we just dump half of this cohort, then reduce the weight a little bit. Now, how much weight I reduce? The weight will become like from m, number of messages will from m to m over 2, right? Or the weight will become from r to r minus 1. Actually, actually 2 from m is equal to n r, right? So it's like from, oh, sorry, like basically here, or maybe just look at here. Then the m will be like from 2 to the n r to like 2 to the n r minus 1, right? Or in other words, like my r is actually changed from r to r minus 1 over n. So as n goes to infinity, again, like this is like the change is infinitely small, so therefore it doesn't matter. So then, and as long as we do that, like we can make sure that like for each of the message for this particular cohort, the probability of error is bounded by 2 delta. As delta goes to 0, 2 delta also goes to 0. Therefore, we are still fine. Yeah. So it's a little bit like caveat for this one. So okay, that's it. Like that's all I like to talk about for the channel coding theorem. As I said, I will skip the commerce proof. Like if you're interested, that's it's on the notes. Like yeah, you and on the book as well. If you kind of like basically very similar to the commerce proof for source. Oh, I shouldn't say very similar, but also use panel and the the steps are similar. Not of course I not completely the same. So okay, so what I'm going to do next, uh, uh, I like to spend some time like talk about feature information, uh, and Cramer Rao lower bound. So we are going backward in time. Actually, feature information is older than the channel information, and they look at different things. And but sometimes it, for some application it may be more useful. Mostly is the criminal rail lower bound. Like that is the focus I like to talk about. So uh, for information, like for example, like for mutual information, or I should say, for feature information, we focus more on like have some oscillation x, and we are trying to estimate some parameter theta there. So you can think of this as like, of course, it's x and theta. They are, if you think of both of them a random variable. If x and theta are more related, if like the mutual information is higher, then we expect the estimate. Let's say like x will be like more useful information in estimating theta, right? Or like if you think of like h theta given x, let's say if h theta given x is equal to 0, then I know that like theta can be determined deterministically as long as x is given. But other than that, like this like mutual information and the conditional entropy do not give a very precise description of an estimator. An estimator in the sense like, let's say I have an x here, I try to create estimator tx to estimate theta. So if I want to get an unbiased estimator, probably I should have like the expectation of tx should be equal to theta. And also like, of course, not all unbiased estimators should consider the same performance even though they are unbiased. So the ones have high variance should be worse, right? So for example, like if I consider variance of the estimator for x, if this variance is farther away from, is larger, then in the sense that a larger chance that it will misclassify or like have a larger error from theta, then it will be worse, right? So in general, I for a good estimator, I would like to have the variance to be small, right? So basically, like the Cramer Rao lower bound have a very nice uh, result is related to the feature information. So it's saying that like if you have consider any unbiased estimator, so in the sense like if I'm trying to estimate theta, that means that like I have the expected value of like Tx is equal to theta, then the variance of this um, Tx here will be bounded by the 1 over the feature information, something like this. So, and this is like, oh, sorry, like this should be like this way, of course, right? So the variance will be like lower bounded by 1 over j theta. So if you think of like, this is like some kind of, therefore like it looks like some kind of information as well. Like if this is like, have like more, you can think of like maybe a better way to write this, because like theta also depend on your observation. Maybe I like to write like this. Like, well, regarding like x, in estimating theta, if this Fisher information is bigger, then you have a you can get a better estimator in terms of like lower variance to estimate the theta. And also the very nice thing here is that you get a very precise kind of like description here. And also like when the lower bound is satisfied, then you know for sure you get optimum estimator, right? So if like I have an estimator t here, if it turns out like the variance of this estimator is equal to the Cramer Rao lower bound, then I know I don't need to do anything further because I cannot find any other estimator will do better than this. Like this is guaranteed by theorem, by theory. That's really nice. And again, I have a crying baby problem. I hope you guys didn't. Yeah. Um. Yeah. I don't know how how loud it get into the mic. Yeah, but yeah. So my wife is trying to tackle that. So okay. So okay, now we can get to this is basically what I like to talk about here. So now we can introduce okay what's visual information and then show the Cramer Rao lower bound and then maybe give an example, like simple very simple example for that. So and to talk about the visual information, it's very unfortunate. I need to introduce this visual score. I don't find that a very intuitive way to explain that. Like it's like something um um I find that myself is a doesn't find this a uh any kind of like good way um to kind of like uh introduce this, I would say. So you just think of like okay, this is some definition like given this way. So think of like you have like a family of distribution. So I have like f oh, okay, okay. Here, I'm thinking, yeah, maybe, yeah, my notes use F. Let me use F is okay. Like, even though my rest of the class I use, so it's like just a PDF here, like, so it's a PDF here. So it's a PDF of X parameterized by some theta here. So, and we say a Fisher score, uh, usually denoted by V here, is essentially just if you think of like uh, the change of um, this PDF with respect to theta, that basically partial f partial theta here, and you want to see like the rate of change of that, therefore like the rate of change of that with respect to fx theta. um, and okay, that would be the Fisher score. So okay, so it's essentially the rate of change of your PDF with respect to theta. And note that like the physics score is defined as a random variable. Here, like I will consider this is of course this is a distribution of the fx theta, right? So, but of course, if I think of x itself as a random variable, then v itself a random variable, right? So think of like I have a fx of this partial fx theta partial theta fx theta. So have this kind of distribution, and each time I sample x here, so then I will have a different v here. So that will be I will have a random variable of v here. So v therefore like this Fisher score here will be a random variable. This is something very important. And for that, I can also write this as a partial log fx theta partial theta, right? If I take partial derivative of that, I will get fx theta, and then take partial derivative, I get partial fx theta partial theta, right? So this is same thing. So, but yeah, I think maybe this is a little bit more intuitive. Therefore, I start with here. Now, what's the theta itself? This this definition is pretty obscure, but if you look at it has like a lot of nice property. First of all, if you look at the expectation of that, this is actually equal to 0. So this is very easy to show. So if I look at like the expected value of V here, this is equal to like partial f x theta partial theta 1 over fx theta. Okay, this is just the V here, right? And then I have like fx theta d theta. That's the expectation, right? Oh, sorry, dx, not d theta, dx. Now then this one got cancelled here. And what I get is I have this integral partial x theta partial theta dx. But then if you look at this integral, like this integral like dx, this x here does not depend on theta, right? So I can have like this partial derivative going out, and I have like fx theta dx here. Then this, of course, okay, maybe I should pause a simple question. What is this? Yes, what was that? Oh, yeah, yes, this is a PDF, like so. Yeah, it's one. Yeah, this is just one. So therefore, like that will be 0, right? So because this is just a constant, partial derivative of theta is just equal to 0. So that one very nice property. If you define v like that, then like the expected value is just equal to 0. Now let's look at the variance of v here. The variance, okay, the variance of v. So because I have 0 mean, it's just equal to expected v squared, right? And actually, I cannot do quite far for that, but here, that's essentially, this is the visual information. That's what we define the visual information is simply the variance of the score. That's the visual information. And now let me give, before going to the Cramer Rao lower bound, let's give some property of the visual information. So in the sense that you can see this, it has some, at least some notion or like some property that appear like the information. So for example, like if I think of like I have let's say what's the visual information of like more than one observation, like n independent observation, like this is like all independent observations, what will be that? So let's see, if I have that so instead I'm going to tackle this directly. Let's consider like what is vx1 up to xn first. So if I have like more than one observation, let's say I have n observations here, my vx1 up to xn will be like partial theta, let's see, uh, log x1 xn, right? Okay, sorry, I'm missing the f here. Now, if they are independent, then I would have log fxi or something like I sum over, maybe I write like that. And that would be equal to like partial, maybe some. Now, if you look at each of these, this is just like the score for xi, right? So then if for the score, like if you have like x1, x2, x3, x4, xn, and so on, if you have multiple scores, then scores of a joint a multiple samples and independent samples will be simply equal to the sum of like these scores of these independent samples. And then if you look at the expectation, like I have this here, look at the expectation of this score of x1 up to xn here. Then okay, this will be what? Yeah. You can actually. You should know that by heart. Actually, this expectation is linear, so you have like this. Because you after all, this expectation is like it's just an integral. Like integral is linear, right? Or like summation. Like integral in this case because this is PDF. Mm, yes. It's just zero. Yeah, it's here. Yeah. So individual of them is equal to zero. So actually, therefore, you look at the score of the entire thing is zero as well. Now we can look at the visual information of this joint thing now. If I have like consider n independent samples and my computer visual information of that one, that will be, as from the definition, is a the variance of like the score v1 vn, right? Or like in the sense that it's actually it's an expectation v x1 xn square. Oh, sorry, what I want to write is a variance of v x1 xn, right? Yeah, but anyway, so this is like equal to this way, and and because I have this property here, the score is just equal to sum of score. Maybe I can emphasize this right here now. Sum over vxi here. So then this equal to expectation sum vxi No, actually, I claim this. Like, why I can do that? So you think of like for each of these v, when your x are independent, your v only depend on the x. For example, your v x I only depend on xi, right? So when xi, let's say xi and xj are independent, vxi and vxj will be independent as well, right? So therefore, like the the product term there, okay, maybe maybe let me write down the product term there also. I have like vxi, vxj as well. Some of these terms there's a 2 or something like this here. But when you do expectation of that, this guy independent. When they're independent, your expectation. Okay, again, like this is another thing. Like if you don't know, still don't know now, like it's important to know. This is equal to ex ey when x y are independent. And this you can very easy to show that. Actually, when this condition is satisfied, when they are not independent, you will just call this uncorrelated. So therefore, uncorrelated is like a weaker condition than independent. Um, yeah. So, but anyway, so and you for independence, you think of like for independent, like this will satisfy. So therefore, like this is equal to if we do expectation here, you have expectation vxi, expectation vxj, and then sum over that, right? Something, and each of them is equal to 0. So therefore, like this term will be gone. So the only thing behind will left behind, therefore, will be just this part here. So therefore, I can just claim this is equal to this one. And then if I look at that, like each of these guy is just the Fisher information, right? So it's like just Fisher information for xi. So therefore, it's actually pretty nice if you look at this here. This in this have like some favor. I mean like of information. If you think of like you have n independent observations, then the Fisher information of this n independent observations will be equal to the sum of Fisher information of each of these observations. So okay. Now let me let me write down some. This is a little bit messy. Maybe I just write down some of this result here so that like you won't get lost, at least completely. So so we have like V itself is defined as a partial log fx theta partial theta, and expectation of V is equal to 0, and variance of V, or like, so therefore like expectation of V square is the Fisher information. That's one variable case. And then if I have like looking at multiple observation, like the score of that, or like the expected, the score of this one, maybe I simply write j theta x1 xn is equal to sum over j theta xi. Okay, let's just keep this. Like keep this a couple of them that for your reference here. So now we start to show the Cramer Rao lower bound. So as I said, like the Cramer Rao lower bound is basically saying that like if you have a unbiased estimator, so let's say Tx, this is a unbiased estimator such that so it's unbiased, so therefore like this is estimator of theta, this is equal to theta, so this implies unbiased, right? Given this unbiased estimator, any unbiased estimator for any t such that is unbiased, then the Cramer Rao lower bound saying that like the variance of Tx here, variance of T or simply write variance of T here, will be lower bounded by 1 over j theta x. So it turns out the proof is like quite simple, like it's like it does not have actually confusion in one slide. So it used the Cauchy-Squash inequality. So if you Cauchy-Squash inequality, of course, there's many forms for that. So one of the form will be if you think of the expectation like x minus expectation x, y minus expectation y, let's say. This is the cost correlation, more or less, will be less than equal to the expectation x minus expectation x square. Let's say I probably have need a square here times expectation y minus expectation y square. So this is Cauchy-Squash. Inequality. So it's one of the format. That's a many form for that. Like, yeah. So in general, like yeah, it's very neat actually. Yeah. So so from here, let's see. If I consider like x and y as like t and v, let's say like instead of like x and y here, I consider t and v here. So I have, let's say, let me just maybe divide, use different color here. Okay, maybe still use the same color. Let's say if I use t and v instead, like times v minus expectation v here, v, right? So this is generally true like for any random variable, but in this particular case, I pick t and v here. So I have this Cauchy-Squash inequality. Now, if I look at the right-hand side here, so maybe I start one by one. So what think of this, like think of this one here. This one, of course, is just variance of t, right? So okay, this is variance of t. So this is I already like see this here, like that's very nice. And like for this one, okay, for this one here is variance of v, right? Variance of v here. And by the way, what is variance of v again? Yes, yes. Oh, wait. Yes, variance of V is J. Yeah, okay. Okay. And by the way, like variance of V cannot be zero because like V is a random variable. If like it's zero, then like you have things is deterministic. So here variance of V is J, like because I V is zero mean, so expectation V squared is actually variance of V here. So this is actually just J here. So we already have like two of the components. So it means like this better to be equal to one, then we are done. So let's see. Um, for the left hand side here, I have like expectation T T minus ET, right? And multiplied by V minus EV and square of that. And let's ignore the square first. I just look at this one here. Try to expand that. I have like expectation TV minus expectation T V minus expectation V T minus expectation T expectation V, right? Sorry, this is a and we'll do the expectation here. Your expectation TV. And if you go down each of this term, you have expectation T, expectation V, right? I might have an expectation V, expectation T. Oh, that should be plus sign here, plus expectation T, expectation V. So I got one of these cancel. I have minus expectation T, minus expectation V here. And so do you still remember, okay, what's this here on this side? What's this? Oh, you want to take a look of this side, like that's here. Yeah. Yeah, expectation T, expectation V. Yeah, I'm sorry with my handwriting. What's this one? Yeah, it's zero, right? Because I expect expectation of V is equal to zero. Now only look at this term here. ETV, this we cannot, probably cannot just simplify here. We need to go into the definition of T and V. So I have basically expectation TV will be just taking an integral here, T of X, and V will be partial F X theta partial theta, 1 over F X theta. So this is V here. And and I do an expectation, so I need to multiply by fx theta and dx here. So this got cancelled. And then I have, again, like similar to before, like I have, this is a partial derivative over theta, but like it does not depend on, the integral inside does not depend on theta. I can pull out the partial derivative outside. So then I have like tx fx theta dx. Now, okay. So see if you guys can see this. Like, what is this? This is on this screen also, but you need to look around. This is not on this side. Yeah. Look around. Yes. Nice. Yes. This is just expectation, right? Yeah. This is really just expectation of f x theta, right? Oh, sorry, no, f x theta. What I'm saying, what I'm waiting. I'm sorry. Expectation of like tx, right? Is height y t is just equal to theta. So this is equal to theta. So partial theta of theta is therefore is just equal to 1. So we are done. Like basically, this guy's 1, 1 square is still 1. So therefore I have 1 here. This is like variance of t. This is like the Fisher information. Therefore, I have like the variance of t is bigger than equal to 1 over the Fisher information. We only need, I only use half of the slide, like both step you get this proof. So let me just end this with a very simple example here. So I have let's consider so let's consider a very simple case. Let's say I have uh, a fx theta, or like it's just a Gaussian PDF. Gaussian PDF with cover unknown mean. Okay, this is mean and variance, right? Sigma square, mean and variance. Let's say this is long, this is unknown. So I know the variance is sigma square, but I don't know whether what is the mean there. So let's say I have some oscillation like x1 up to xn, let's say, okay? And then given n samples, I'm trying to estimate the mean. So okay, what will be an estimate for that? Like just I guess it's like I have like let's say mu hat is equal to this estimator of x1 up to xn. This is my observation. And I'll say, okay, one very simple and reasonable estimator that you all use and know will be just taking the average of your observation, right? So I'll estimate the mean as a x1 plus x2 and xn over n, right? So this is my t. Like, okay, you can define other estimator, but this probably like the one that you used before. I would say, right? Very simple. Like, is that clear what we are doing? Like we just have like a normal distributed sample with a unknown mean, but the variance I know is a sigma square. Now I got several samples, like n samples, like x1 up to xn, and I'm trying to estimate the mean. And hopefully it won't be surprising to you, like the canonical, I would say, estimator for this problem will be simply computing the average, empirical average of this sample, say x1 sum to xn over n. Now we want to show that this is like the optimal estimator. So we can use the Cramer Rao lower bound to show that. So as long as we show that the variance of this estimator reach the Cramer Rao lower bound, then we know that this is the optimal estimator, right? So let's see. maybe first let's compute the variance of this guy. Like what's the variance of this? Variance of t here. The uh the of course for this one, this is a maybe I even need to show this is an unbiased estimator, but I hope it's obvious. So if I do expectation of t here, it will be expected value of like x1 sum to xn over n, right? So expected value for each of these will be like expected x1 plus expected x2 and so on and so forth. Sum up to expected xn over n. Each of them is equal to mu, so I have like m mu over n. So then indeed like this is an unbiased estimator. It get estimated the correct kind of like estimate here. That's what I want. Like I want it to estimate to mu. Now, let's think of like the variance of t now. The variance of t, this one, so will be, let's see. Let me write the notation here. Let me write mu hat here. Okay, I already have mu hat. Mu hat written as the empirical average of this n samples, right? So now the variance of t here, or like it's actually equal to the variance of mu here, mu hat here. So it's equal to the expected value of mu hat minus mu square. And I have, I can substitute that like x1 plus xn over n minus mu square, expected value of that, right? And maybe better to use a summation here. So let me write this as a summation xi 1 over n here. And I can think of this as like 1 over n mu also. I put a sum here. So then like this I can group together to be like this, and square of that, expected value of this. Okay? And is equal to 1 over n, expected value sum xi minus mu square. So for each of this guy is equal to sigma square, right? So I have, let's see if I, wait, I have a mistake here. Oh, okay, this is n square, I'm sorry, like, yeah. So this is 1 over n of this, that's a square, this is n square, yeah, that's good. So now I have like each of these guy, let me write one more step, n square summation I from 1 to n, expected value xi minus mu square. And this is just equal to the variance of wait. It's just equal to variance of x, right? So therefore it's just equal to sigma square. So therefore I have like n sigma square over n square, therefore it's equal to sigma square over n. Okay, so for this estimator, my variance is therefore is equal to sigma square over n. So maybe I just put it here. Variance of t equals sigma square over n. Now, if I show that the Cramer Rao lower bound that is also like sigma square over n, then this basically show that this is the optimal estimator. Then, and also like there's nothing we can do better than like just taking the simple empirical average. So let's see. So let's compute the feature information, and then we'll be able to find the feature. Then the the Cramer Rao lower bound will be simply the inverse of the Fisher information. So for J, so let's compute J mu x1 up to xn there. Now, first of all, like I know that like earlier, this will be equal to nj mu x, right? Because if they are independent, I have an independent observation, then the Fisher information of that will be simply like n of this Fisher information, Fisher information. So I can compute individual of this. So for this one, mu x here, j mu x is equal to the variance of the score, and the score is, or the expectation, expected v square. The score is like partial derivative of mu, and the PDF, okay, of like f x theta, right? Square. I'm missing a lock here, and it's equal to expected value partial mu. Sorry, not theta here. This is mu here. And the PDF for Gaussian will be like 1/2 2 pi sigma square exponential minus x minus mu square over 2 sigma square. And like that, the whole thing I should square this, something like this. Now, if I take, it looks ugly, but once I take the log, it should be much simpler. So I have like partial mu. Take a log there, I have like minus log, I guess minus 1/2 log 2 pi sigma square. And then I have like minus x minus mu square over 2 sigma square. Still have a square here. Oh, actually, I don't even need that. I take the partial, take mu here. This is gone. I don't need to care about it. For this one, I take the partial derivative of mu there. Sorry, the square should be outside. Partial derivative of there, I should get expected value 2x minus mu. Yeah, over 2 sigma square. And then I have the square again. So then this will be equal to 1 over sigma fourth expected x minus mu square. And again, maybe another simple question. What's this? Yes, that's variance. Variance of x and variance of x. Yeah, so therefore it's just sigma square, right? So this is sigma square. So it's like sigma square over sigma fourth. So it's like 1 over sigma square. So therefore the Fisher information is like 1 over sigma square. Therefore, like if you look at like the Fisher information of like, okay, of like n observations, will be n of this like sigma, or n of this Fisher information of only one observation, right? So therefore, like this will be having n observation will be equal to n times j mu x equal to n times 1 over sigma square, or like n over sigma square. And then like now finally the Cramer Rao lower bound, so therefore it's just equal to 1 over j, right? J theta x1 up to xn is just equal to sigma square over n. So and this indeed is like the same as this one, right? So our very simple estimator already reached the Cramer Rao lower bound. So therefore, like there's no way we can improve that, and that's it. So okay, this is like more or less I like to talk about for Cramer Rao lower bound and visual information. This is a short, but I think especially if you guys have work on estimator, this is like something you would like to know at least that in some cases, of course, it's not easy. What I mean is like it's not guaranteed that like there's a I mean there's the Cramer Rao lower bound can be reached by some estimator. It's possible there's no such estimator, but at least that gives you a sense of how good you are um, away from the theoretical limit. So if you're pretty close, then like maybe it doesn't help like to spend like too much effort like to try to get even better estimator. So okay, this is like quite odd work. I have like 10 minutes, like something like I don't know what to do. Uh and by the way, like do we have a class on Thanksgiving? Like typically not, right? Let me check. I remember it's like I don't incline to have class on that week. So then like if we don't have a class next week, then maybe we only have one more class, I guess. Uh, yeah, I think like next week is actually a an holiday. Oh, I didn't know that. I give you an assignment during a holiday. So it's not exactly an assignment, right? So it's up to you whether you want to do a correction for your midterm. Like if you think it's good enough, especially if you get over 30 or 40, I guess it's up to you. But of course, if you get that high score, then you probably don't need to do much to get even higher. Uh, yeah, you. So, but anyway, I guess that's better. Like because if I just talk about the solution, I guess it's probably just waste of your time because you don't have any incentive to digest them. So yeah, and so I let me see. I actually because I only have one class left, it looks like um I I think most likely I'm not going to talk about MCMC because we don't have much time left. Um, I'm thinking like I may just give a very short introduction on Leo. Is that Leah? I think it's a Leah. I think. So it's like a um probabilistic programming package. Like it's not something like extremely popular and something like the state of the art, but like is something like can be quite handy if you have like simple toy problems like such as our homework assignment. So I may give a little bit time on that because after all the title of the course is like related to probabilistic programming. I feel a little bit um kind of like uncomfortable. I actually because in the past, some of you guys at least will talk about like some of these packages um in the presentations, but this time no one picked such options. Um, so maybe I will talk a little bit about that. And besides that, I probably will spend some time on graphical models and Bayesian networks. Not a lot of time. Maybe I can even start a little bit now. So maybe just uh, to give a feel. Like so basically like you if you think of like when you have a larger problem, have more and more random variables, um the structure of the random variables are important. If you have like let's say 100 or 1,000 of random variables, and if you just like consider all the combinations without looking at the constraint of the random variables, then the dimension would be much higher. Like the the space you need to consider will be much higher. Let me give some very simple example. Let's say if I have like a couple random variables like x, y, and z here. So if I consider them to be independent, then to uh let's say let me just let me see. Let's say like if I have like four values for this guy, four values for this guy, and four values for this guy, right? Now, if they are independent, so I need to describe this entire problem. Like when I describe the entire problem, what I need to know is like just the joint probability distribution. Right? Once I know the joint distribution, then I know everything, right, essentially, of the all the statistics. So if they are independent, so I only need to know the marginal distribution, right? So in this case, I for this distribution, like I have four values here. Um, then the probability, like you can say like I only need four parameters here, or maybe three parameters. Uh, if you count that, like because you need to make sure the probability of like all of this x sum up to one, right? This will sum up to one, right? So maybe I can count like this is three parameters here. Also these guys will be three parameters, these three parameters. So in total, I will need nine parameters to characterize the entire problem here, or the entire distribution here. But instead, like if I don't have this constraint, then I will assume that it can be any uh, these variables. It doesn't need to be independent. They can depend in whatever way, in whatever ways. Then I basically, maybe I'll give you a question. Basically, how many parameters do I need? Maybe this is the last question, I guess. If basically characterize the joint distribution. Here I'm characterizing the joint distribution also, but because they're independent, I can just each of them, like consider them each of them like independently. So for the marginal distribution of this guy, I need three parameters, this one three parameters, this three parameters. So therefore in total nine parameters. So now if they are not independent, like how many parameters in general do I need? No. So I guess yeah, because we're running out of time, I guess I'll just answer myself. So so if I don't have any constraint, mm, it will be more, right? It will be more, it will be more, much more. Actually, if I don't have any constraint, if they are not independent, it means that, or like, if they are not independent, and also it doesn't have any kind of constraints with the random variable, then I'm only considering the joint distribution, right? So here, like, the joint distribution can be decomposed into just like PX, PY, and PC. And I can characterize each of them independently, right? So therefore, each of them just need 3 of them. So therefore, I only need nine of them. But on the other hand, if I, in general, I cannot decompose them, then I have like X, each of X, Y, Z, each of them have 4 different combinations. So then in total, like I will have X1, Y1, C1, and X1, Y1, C2, X1, Y1, C3, X1, Y1, C4, and then X1, Y2, C1, and so on and so forth. Like I need to characterize all the probability, I mean, the probability of all these combinations here. And the number of combinations will be 4 by 4 by 4. You can minus 1 because that's a constraint that sum of all these probability equal to 1. But essentially, this is like 63, right? So it's like much, much larger than this one. So therefore, like the relationship among the variables are important. Like whenever you have relationship there, and it's obvious, you should take advantage of that. Otherwise, you're kind of like the number of basically the capacity of your model increase significantly, also exponentially. And the problem is it's kind of a classic like machine learning problem. Basically, if your model is too complex, then you will overfit the model, right? And also you will need like way more data to train your model. And if you can kind of like right away you realize there's some relationship about the random variable. For example, like I know that y is like kind of like x and z are conditionally independent given y, then I should put into that into account. And so ultimately, a graphical model, what it's trying to do is like we want to like have just like a graph. You can think of graph model to write down all the random variables, and hopefully from that graph, it will deduce all the relationships. The relationships will be like whether a variable is independent with another random variables, or like a random variables is conditionally independent with another random variables. And hopefully from that graph, just simply drawing the graph, it can deduce all these combinations. And and of course, you should put this combination into account when you compute, trying to characterize the model. So anyway, I'm continue this next time, and yeah. So I'll see you guys after the holiday. So happy Thanksgiving, and I will see you guys in 2 weeks then. Yeah, I probably will put up another homework assignment. Yeah, thank you. Till I don't know, uh, maybe yeah, maybe two at least 2 weeks ahead. Like yeah, probably post an assignment like quick. Will be the last one. So and yeah, and yeah, thank you. So see you guys then. Yeah.